Hi everyone, and welcome to a section of advanced topics notes. We're doing 5.3 special factoring. So we got all different kinds of special cases here today. We have difference of squares, perfect square trinomials, difference of cubes, and sum of cubes. We're going to get to all of these, so hang in there. Let's get started. Now, difference of squares. When you recognize something like this, it doesn't fit in our typical pattern of two binomials, or at least our typical formula, our typical procedure of how we factor, because there isn't a middle term. Usually we have a first term, and we know that these two multiply to give us a first term, these two multiply to give us our last term, and the sum of these give us our middle term. But there's no middle term, so what do we do in this case? This is a special case. This is a special case where the middle term cancels out. The middle term cancels out because they are opposites. For example, if we have this is x, and this is x, and then this is y, and this is y, one is positive and one is negative, and this is how we factor this particular case, known as difference of squares. Now, it's important that it is in a certain pattern, and that pattern is that it has to be one square subtracting another square. Okay, what do I mean by square? Well, a square could be x squared. For example, you can take the square root of x squared, and it's not going to be an irrational number. It's just going to be x. For another example is we could have something like 16. We take the square root of 16, we get 4. Okay, so these are all examples of squares, and this is how we factor it. Okay, now let's put it into practice. If we have something like this, t squared, and we have here a 36. First thing we should recognize is, okay, 1, are these both squares? The answer is yes. We have a square here, and technically this 36 could be rewritten as 6 squared. So they're both squares. Second thing, are they a difference? Is it subtraction in between those two squares? And it is yes. Yes, it is. So we are ready to put these into our difference of squares factoring, where we put t squared, and we'll take the square root of that, and that's t. That t will go here and here. Okay, let me highlight that just to make it a little bit more obvious. Here and here, we put the t. We take the square root of the second term. Okay, this is the second term. This was the first term. In case you don't remember, that's the first term. Then we take the square root of the second term, wrong color. The second term, square root of 36. And that is 6. We're going to put that 6 here, and we'll put that 6 here. Okay, as a reminder, this is the green. Okay, the second term. Second term goes in the second slot. And we make one positive and one negative. It doesn't matter if the first one's positive and the second one's negative, or the first one's negative, the second one's positive. Okay, but that's how we do it. Okay, so then we look at all of these, and we're going to apply the same principle. So is this first term a perfect square? The answer is yes. It is a perfect square. So if it is a perfect square, we're going to put the square root of that first term in those two slots. Well, the square root of 16 is 4, and the square root of m squared is m. So it's just 4m for both those slots. Then we're going to say, okay, let's do the second slot. Is the second slot a perfect square? It is. The answer is yes. Okay, you can take the square root of 49. You can take the square root of p squared, so it's a perfect square. We're going to put the square root 7 of the coefficient, and then p is the square root of p squared. 7p, 7p. We'll make one positive, one negative, and there we go. Now that is in factored form. Okay. Now you can also check your answers with FOIL. I forgot to do that here. Let me check the answer. We multiply the t times the t, and we get t squared. Then we get minus 6t. Then we get plus 6t, and then minus 36 because it's positive times a negative. Notice what happens here. This is what I was talking about. These end up canceling each other out. They go away, so we're just left with t squared minus 36. Difference of squares, thus its name. Last one. Actually, I went in the wrong order, but I guess it doesn't matter. Here we have a perfect square. Here we have a perfect square. So in our first slot, we're going to put the square root of 4a squared. In the second slot, we're going to put the square root of 64. Let me go ahead and make my parentheses now. Look at that. I did it. beforehand. So we have 4a, wrong, 2a, 8, 8, make one positive, one negative, and there you go. Okay, that's all there is to difference of squares. Recognizing it, I think, is the tough part. Perfect square trinomial, this is a special case. Anytime you see a square term in the front for the first term, let me be consistent with the colors here. So the last term has to be a perfect square, okay? The first term has to be a perfect square, all right? And then the middle term is the sum, sorry, it's double the first times the last term's square root. So we take the square root of the first term and the last term, xy, and we double it. Now, it seems more complicated than it actually is. I know you're thinking, whoa, what the heck? That's a lot to remember. Okay, it's not that bad. Once you put it into practice, it makes it much, much easier. Okay, so first thing, if it's a plus plus, you know both of these are going to be plus. Okay, and then essentially what we're doing is because of this pattern, okay, we have x squared, so we're going to take the square root of that, put it in the first slot. We're going to take the square root of the y squared, put it in the second slot. Okay, and this middle term is a result of double x times y, okay? The square roots, double them, the product of those square roots. Why is that? Actually, let me move this down a second. The reason why that works is because if we multiply our first terms, okay, x squared, last terms, of course, y squared. That's why we take the square root of those, just like before, okay? But if we multiply our outside and inside terms, we get xy and xy. What happens when we add xy, we get 2xy. That's where the middle term comes from, is the product of the square roots of those two terms, okay? Now, if we have x plus y times x plus y, we can rewrite that. It's x plus y times itself 2 times. So what we do is we change this to become x plus y squared. And that is why it's called the perfect square trinomial. In a very similar token, we have the second example. And in this second example, it's very similar, okay, except we have x, y, but now it's a negative double the product of the factors. And the way that comes about is if both of these are negative. So it's x minus y times x minus y. That's still a perfect square trinomial. It's just negative, so we square it. And this is our little framework for a perfect square trinomial. Okay, let's go ahead and do a couple examples, and then I'll send you on your way. I think we're going to do difference of cubes in a second video, part 2 for this. So we have x squared minus 8x plus 16, okay? First thing you should recognize, is this a perfect square? Yes. No, I got the wrong color. Let me do blue. Is this a perfect square? Yes. Is the last term a perfect square? Yes, it is, okay? Is the middle term, wrong color again, is the middle term the product of the square roots of those two terms? Doubled. So again, double the product of the square root of x squared times the square root of 16. Is that the case? Well, square root of x squared is x, square root of 16 is 4. 2 times 4 times x is 8x, so it is the case. So we can rewrite this guy as x. Okay, notice this too. If it's minus here, it's going to be minus inside our parentheses here. X minus, and then it's going to be 4. And technically we're going to do that twice, so we can square it, and there is our answer. Now, let's say you're trying to factor this, and you don't even recognize that this is a perfect square trinomial. Technically, if you're just factoring like normal, where you put the x and you think of factors of 16 that add up to negative 8, and you're like, okay, I know it's negative 4, this is minus 4, minus 4. Technically, this is the same thing. And then you can be like, oh, I just factored it, and I recognize, oh, I wrote the same thing twice. Now I can write it like that, where I do x minus 4 squared, and it's the same thing. So really, you don't have to worry about memorizing this too much. Just recognize anytime you have x minus 4 times itself twice, it's going to be squared. Now, here's a great example because this one's a little bit different. Number one way to do this problem is we could divide everything by 4 first and factor out the 4, 20a plus 25. And then we could go from there and factor it like this. Okay, I'll show it this way and then I'll show you the other way from the beginning. Actually, let me show you. I'll come back to this way, put it off to the side, and I'm going to show you how we would do it normally. Okay, so then how we would do it normally is we recognize, okay, is 4a squared a perfect square? Yes. Is 100 a perfect square? Yes. What's the square root of 100? The square root of 100 is 10. What's the square root of 4a squared? It's 2a. If I multiply 2a times 10, I get 20a, right? 2a times 10 is 20a. If I double this, okay, if I double this, I don't get 80a. So this by itself is not a perfect square trinomial. We would have to factor it a different way. But if we look at this guy, okay, maybe this one is a perfect square trinomial. So let's try this again. Okay, we have 4 out in front. We have a, we have the square root of 25 is 5, and 5, whoops, I meant to do it like this first. Okay, if we multiply 5 times a and then double it, we get 10a. This one is not a perfect square trinomial either, okay? So example 5 is kind of tricky. It's not a perfect square trinomial. So that's interesting. A perfect square trinomial, this number would have to be a 4, and then it would be, okay? So actually, I'm going to change this one. So it is a perfect square trinomial. So then we have the, here, let me go like this, squared. Okay. So then we're going to take the square root of 4a squared, that's 2a, and then 100 is 10. 2a times 10 would be 20a, and then we would double it to get the middle term, which is 48. We changed it so it would become a perfect square trinomial, and then it would be plus. So if we wanted to make a perfect square trinomial, that's the way we would do it. I don't really want to show how to factor. I think it would be a waste of time at this point if the original problem, just because I want to make sure that we recognize what is a perfect square trinomial. So go ahead and change that to a 40 for now. I think that makes a little bit more sense in context. Last one, which of the following are perfect square trinomials? We already learned that example 5 was not how it was written. Okay, so what we're doing here is we're looking for, first, do we have squares here? Okay, and the second thing, do we have squares here? And more importantly, is the middle term double the product of the two square roots? So the square root of 4 is 2. 2 times 2 is 4. Okay, this one is, yes, it is a perfect square. Okay, and if we were to write it, I guess I'll do this too. We would get x minus 2 quantity squared. Yes. Number 2, the square root, the square root of 25 is 5. The square root of x squared is x. 5 times x is 5x. Double it, we would get 10, okay? But we would make sure, because it's minus, again, we go x minus 5, quantity squared. Is it a perfect square? The answer is yes, it is. Okay? Then we have x squared plus 6x minus 9. Let's take the square root of 9 is 3. Here's something, though. Look at this. What's the square root of negative 9? See how there's a negative sign in front of it? Anytime you have a negative sign in front of the third term, it's impossible to take the square root of that. Square root of negative 9 is actually 3i, imaginary 3. So this one is not an imaginary, or excuse me, this is not a perfect square because you can't take the square root. Now, this one at first glance does not look like a perfect square trinomial. So let's divide everything by 2 and see if that changes anything. We'll factor out the 2. We have 2 times x squared plus, divide everything by 2, 6x plus 18. And we recognize that it still is not a perfect square trinomial because 18 is not a perfect square. So this one is not a perfect square trinomial. You could also see from this initial setup that 36 is a perfect square, but 2x squared is not. So that is a no. Hope you enjoyed this video. Stay tuned for part 2, difference of cubes and sum of cubes. I know you'll enjoy it.